So there's like, what are there? I don't even know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different types of acid-base problems. So really the point of this is to be like, okay, if I read this problem, what do I do? Okay. So before I go through these examples, I'm going to point out what each thing stands for. Okay, so if I have it written as HA, that is a weak acid. Whereas H plus means a strong acid. Okay, so yes, you do have to know your 6 strong acids still. Assume every other acid is weak, but weak acids mostly stay together. That's why we write them as HA. And then for bases, B is a weak base. Fine, so weak base, and then a strong base is just OH minus, because all of the strong bases have OH minus. Okay, so you need to look at what is being added for each one and what is going to affect the pH, because most of these will be like, what's the pH of blah, blah, blah. So we're going to start out pretty straightforward, and that's when you have a weak acid in water. Okay, so if you would look at this problem, you'd be like, okay, I just have a weak acid. How do I figure out that pH? Now you can't just take the negative log because it's not strong. So you have to do an ice table. All right. So anytime you see a weak acid, your strategy should be to write your Ka equation because it's an acid and do your ice table. Okay. So I would write my Ka equation. So Ha plus H2O makes H3O plus and A minus. Okay, so you would go through your ice CE with whatever information you have, and then you would solve for X, and then you need this number here, since that's H3O plus. If you take the negative log of that, you will get your pH. Okay, so anytime it's a weak acid, you need to do your ice table. Okay, so an example would be, I'm going to write examples over here. If I had HF dissolved in water, and I said, what's the pH of this concentration of HF? Because that's a weak acid. Now, weak base is similar. It's just going to be Kb. So if I have a weak base just dissolved in water, I want to know how to do that. So an example, and our most common example for weak bases is NH3, or anything that has an NH2 something on it. Okay, so instead of a Ka equation, since we know it's a weak base, we need to do the Kb equation and an ice table. Okay, so Kb equation is like what happens in water. So you might want to practice writing your Ka versus Kb equations. If it's a base, it accepts a hydrogen, so it's going to be BH plus now, and you have OH minus. Okay, so if it's basic, you should end up with OH minus on the right side. That makes sense. That's going to give you a basic pH. So you would do your ice table here. And then once you find this guy, if you take the negative log of that, that will give you your POH, and then you can easily get to your pH. Okay, so this is weak acid and weak base. Questions on those two? Okay, I'm going to move on to the next set, which is conjugates of weak acids and conjugates of weak bases. Okay, so you do need to practice identifying those. Remember, if it's the conjugate of a weak acid, it's like the weak acid after it lost its H plus. So you should be able to identify those. Most of the time we put them with sodium because sodium is always, it doesn't do anything in the solution. It's a conjugate of a strong base, so it doesn't do anything. But this is A minus, right? A minus is the conjugate of a weak acid. So you should be able to recognize that. This is a conjugate of a weak acid. Okay. So this is like a salt dissolved in water type of question. So the question could ask, what is the pH of a solution that has NaF in it? Okay, and you should be able to recognize that F is the conjugate of HF, which is weak. So this is a weak acid. So what you would want to do, or the conjugate of a weak acid. So I could ask, like in a multiple choice question, is this going to be acidic or basic? And you should be like, well, if it's the conjugate of a weak acid, it's going to be basic. It's going to do like the opposite thing of the acid. So if it's basic, we need to use a Kb equation. Okay, so these are like switched from what they were right above. I'm going to go ahead and write for my conjugate base one also. Hang on. BH plus would be the conjugate of a weak base, and the conjugate of a weak base is acidic. So you would have to do a Ka equation. An example of that would be if you had something that has NH4Cl in it. Chlorine doesn't do anything because it's the conjugate of HCl, which is strong. So just the NH4 plus, which is the conjugate of NH3, does something. Okay. Now, the only difference between these two problems and the weak acid, weak base problems is that usually I give you the Ka for the weak acid and you have to find the Kb first. So we know it's going to act basic, so you should do the Kb equation, but I usually don't give you the Kb. So we have to find it from the Kw equals Ka times Kb. Same thing if I give you something like NH4Cl, I'm probably going to give you the Kb for NH3, and you have to find the Ka and then use it. Okay, so this is going to be Kw, same equation, solve for whichever one you need. So if it's going to be basic, okay, like this one up here is going to be basic, you need to write the Kb equation, not the Ka equation, Kb. So I would be like, okay, the Kb equation is when it reacts with water, it acts as a base, and I get OH minus. Okay, so you need to write the Kb equation if it's going to be basic. If it's going to be acidic, you need to write the Ka equation. So BH plus water makes it acidic. It donates its hydrogen, so I end up with B and H3O plus. Okay, so all of these kind of come in twos. They're kind of like opposites of each other. So this is just opposite of the ones right above it. You just have to find the correct K equation. So if it acts like a base, write the base. If it acts like an acid, write the acid. Okay, that's important. So you still have to do an ICE table here. So you can do an ICE. And then once you get to the end, we have this guy is OH minus. So we can find POH from that, negative log of that, which can get you to pH if that's what I'm looking for. And here is H3O plus, so we can get the pH there. Okay, so ICE tables for all weak things and conjugates of weak things. Okay, just dissolved in water. All right, questions on those two? Okay, I'm going to move on. They're going to get more complicated. Actually, the next two are not very complicated. Okay, so this is just if they're in water. Now, we had two of these on the pre-lab. Okay, this is a weak acid and a strong acid. If you have a weak acid and a strong acid together, the strong is the only thing that's going to affect the pH. Okay, the weak is so weak, it's not really going to make much of a difference at all. So all you have to do is find the pH of the strong acid. So this would be like if I told you I was combining HF and HCl, we really just care about the HCl from the strong acid. Now that being said, okay, so we would write pH is the negative log of your H plus concentration. That being said, you're adding two solutions together, so your volume is going to get bigger, which is going to change this concentration. So before you plug it in, you have to do an M1V1 equals M2V2. Okay, so yes, we only care about the hydrogen ions from the strong acid, but if I added something to something else, say I had 5 milliliters of one and 5 milliliters of the other, well, when I combine them, now I have 10 milliliters, so that actually changed my concentration. So you would want to do this first, and then plug it in here. Okay. Same thing is true if you are going to add a weak base and a strong base. The strong base is the only one that affects the pH. So strong base, if this was a weak base, this would be like if I said I dissolved NH3 and sodium hydroxide. All I actually care about is the sodium hydroxide. The weak one's not going to do anything. But we do have to do an M1V1 equals M2V2 first, because again, I'm putting two solutions together, so my volume is changing. So my concentration, excuse me, is changing. So I would find my POH from the negative log of the OH minus concentration, the new one. Okay, and then you could do 14 minus if I was asking for pH. Okay, questions on those two?
So for that, we wouldn't have to like show work like of an ice table or anything like that. We could just do straight up the pH or POH once we find the new concentration.
Yes, exactly.
Okay.
Yep. Now, like you could prove that it doesn't matter if you want to do the ice table, but I won't ask you to do that. If you did the ice table, it wouldn't be wrong. You would end up with the correct answer. It's just more work than you need to do. Okay, I'm going to the back. We're going to get more complicated here. So those were all ones that are just in water and two acids together and two bases together. Now we're going to go on to when I actually neutralize that. So when I'm doing a titration or when I add acids or bases to buffers, that's what this whole back page is for. Okay, so actually these first four have to do with like titrations, or at least the first one's a titration. You might not notice that just right off the bat. Okay, but if you look at this is a weak acid. And I'm neutralizing it with a strong base. Okay, so even if you didn't recognize that this is probably a titration that's going on, you should know that a base is obviously going to neutralize an acid. So before you do an ice table, you first have to do a before change after table for the neutralization part. Okay, so if you're adding two things that neutralize each other, you first have to do a before change after table. Okay, and that's just for the neutralization reaction. So it's like, okay, my acid reacts with my base. So one of my products is going to be water and the other one is going to be A minus. Okay, that is the neutralization reaction. Notice this is not a Ka or a Kb equation, okay, because I'm not adding it with water. So this is just neutralizing. So you have to do this first to figure out how much of this is left or how much of this is left before you plug them in. Or maybe you use all of that and you have OH minus left. It kind of depends on where you're at in the titration. So once you have done this, then you can plug it into an ice table if you want to. But there's kind of some shorter ways to do that. So there's kind of three options. Okay, it's either you might be before you've hit the equal or the equivalence point. So before the equivalence point, okay, or you could be at the equivalence point, or you could be after the equivalence point. Okay, equivalence point would be exactly when your acid and your base have completely neutralized each other. So it would be like 0, 0, and then you have A minus here. That would be the equivalence point. If it's anything before that, you will have acid left over because you haven't neutralized it all yet. And if it's anything after that, you have base left over. Okay, so how do we calculate these? All right, so if you're before the equivalence point, that would mean that I still have some acid left over and I should have some A minus. Now you might notice if you have HA and A minus in a solution, you technically have a buffer. So you can use the buffer equation. So there's two options. You can either do an ice table or you can use the Henderson-Hasselbalch buffer equation. Either way. Okay, but if you are before the equivalence point, so you still have stuff left over, you should do the ice table or the Henderson-Hasselbalch equation. Now, this is an acid and we haven't neutralized everything yet. So you should be using the Ka. It's going to be acidic. Okay. Now at the equivalence point, the definition of equivalence point, like I said, is when these two have neutralized each other. So that would mean that everything that was here is now turned into A minus. So I would have everything turned into over here. So all I would have in solution is A minus. Now, A minus is a conjugate of a weak acid in water. So technically, I have to do what I did up here for when I have A minus in water and do an ice table to figure out what my pH is. So if you have just a conjugate in water, you're going to have to do an ice table to figure out the pH. And no, you can't use the Henderson-Hasselbalch one here. You would have to do an ice table. Now, if I have all A minus in my solution, meaning I've hit the equivalence point, I have only A minus left, then A minus is a conjugate of a weak acid, so it actually acts basic. So you should be using the KB equation. Remember, this is this kind of defines why a weak acid titration curve, the equivalence point is actually higher than 7 because that A minus kind of acts like a base. Okay, so if you're before the equivalence point, you're still acidic. If you're at the equivalence point, you're basic, and everything after the equivalence point is basic as well. Okay, so that one's Ka, that one's Kb. After the equivalence point, you should just have extra OH minus, and whatever extra OH minus you have, you can find the POH from. So this one, you don't have to do an ice table once you're past the equivalence point, just do the POH of like whatever your OH minus is there. Okay, so you have to pay attention to what you have left over. Think about like what's in the solution. Is there acid in there? Has it all been neutralized, or is there extra base in there? Okay, and this would be an example like I had HF, so a weak acid, and I'm adding NaOH. So this is like a titration. Okay, questions on that one? Those are the most difficult and complicated ones for titration calculations. No? Okay, we'll do the base one here in a little bit that's reverse. But before we get there, this one is a little bit easier. You should notice that in this one, I have weak acid. And Na doesn't do anything. So I have A minus here, which is its conjugate base. So anytime you have a weak acid and its conjugate base, you can use the Henderson-Hasselbalch equation. So you should be like, oh, this is a buffer. Just like in the second part up here in the titration, when you have a little bit of both, that's a buffer. So you can use Henderson-Hasselbalch. You do not have to have this memorized. pH equals pKa plus log of A minus over HA. That's it. Okay, so that would be like if I told you I had HF and NaF in a solution. Okay, so the acid and its conjugate. Okay, I'm going to switch to bases unless there are other questions on these two. Okay, usually I have you do titration calculations, and honestly, most of the time we have acid in our Erlenmeyer flask and we're adding base and we know the concentration of base, but technically we could do it the other way around. So that would be like if I had a weak base and I was adding acid to it and doing a titration curve, it would just be backwards. It would start basic and go acidic. So this would be if I had a weak base and I added a strong acid. Okay, so this is a neutralization reaction, right? I have base, I have acid. I have to figure out how much is neutralized before I can figure out the pH. So anytime you're adding an acid and a base together, you have to do a neutralization reaction with a BCA table first. Okay, so my example here would be, say I had NH3, started with NH3, and I was neutralizing it with hydrochloric acid, and I wanted to know what my pH was at a certain point. Okay, so this is like a backwards titration. So like I said, anytime you've got acid reacting with base, this is a neutralization equation, neutralize first. Okay, so like my base and my acid neutralize each other. And I just get BH plus. So it's like NH3 plus H plus makes NH4 plus. So you want to do your BCA table. Okay. So you will either not have added enough acid to neutralize the base. You will have added exactly the right amount of acid and all of the base will have turned into conjugate, or you will have added extra acid. So just like in the titration with the weak acid, now we have, it's either before the equivalence point, at the equivalence point, or after the equivalence point. Okay, before the equivalence point, I would still have some base left and I would have turned some of it into conjugate. So you're gonna have to do either an ice table or you can use the Henderson-Hasselbalch, because if you have both of these guys, it's technically a buffer. Okay, now if you use the ice table, notice this is a base. you need to use the KB equation because at this point you still have more base than you have acid. Okay, so this is neutralization equation. This would be a KB equation. At the equivalence point, okay, just like before, that would mean all of my B, I would have none of it left. It would have all turned into BH plus. So the conjugate, or NH4 plus, if you're thinking of NH3 as the example. If that's the case, that is a conjugate of a weak base, just like one that we did on the front, and you have to do an ice table to figure out that one. Because you don't have both parts, you can't use Henderson-Hasselbalch, but if you have one part, you have to use ice. Now, this is the conjugate of a weak base, so it is going to be acidic. So you're going to have to use the Ka equation because it's acting acidic. Okay, so this is one of those times that I told you is really important to pay attention to if you are writing a Ka or a Kb equation and you're using either Kb or Ka correctly, whichever one goes with which. Okay, so just like in our titration above, if we were doing weak acid with base, the pH is going to be higher than 7 at the equivalence point. Well, if we're going the opposite way, so if I'm doing weak base with strong acid, the equivalence point is going to be lower than 7. It's going to be more acidic because this guy acts a little bit acidic. Okay, then after the equivalence point would be when both of these guys have been neutralized. I got some extra H plus left over, and whatever H plus you have left over, you can just do the pH of, just take the negative log of that H plus and you will have the pH. So essentially, anytime you're after the equivalence point, you just look at whatever strong acid or strong base is left over and you can find your pH. We haven't really done a whole lot of those, so if you have a question on that, let me know. Okay. All right. Now the rest of these are not so bad. I've got B and BHX. You might be, what in the heck is BHX? Well, we know this is a weak base. Weak base. And this is supposed to be like BH plus, like NH4 plus, with some type of halogen, because halogens are never, well, yeah, not never, fluorine could affect it. Usually it's chlorine. It's like the weak base and it's conjugate. It's conjugate acid. So it'd be like if I said I had in solution NH3 and NH4Cl. Okay, you should be able to identify that that's a base and it's conjugate acid. And anytime you have an acid and its conjugate base or base and its conjugate acid, you have a buffer. Okay, so this you should recognize as a buffer because it's got both parts. So we're going to do buffer again. Okay, so you can use your Henderson-Hasselbalch equation. Now, if you want, I can put the KB form of the Henderson-Hasselbalch equation on there because if it's a base, I'm probably going to give you KB. But I like, just since I have this one memorized, I always use this one. Let's see, A minus over HA. Essentially, if you have the KB, we can find the Ka, plug that in. A minus is the base and HA is the acid. So just put the base over the acid and you're good. Or like I said, I will probably put on the KB form of this equation as well, in case you want to use that. So you can technically use either one as long as you're using the Ka or the KB as it describes. So hopefully you can recognize your buffer and then be like, oh, I can plug that into the Henderson-Hasselbalch equation to get pH. All right, last ones. We have got buffers, but like when I actually add acid or base to a buffer. Okay, so the whole point of a buffer is that it buffers the pH and makes it so it doesn't change drastically. So if I have a buffer and I add acid, it shouldn't drastically change the pH to go lower, maybe a little bit, but not much. And then if I add hydroxide, it also shouldn't go as basic as if it was just water. So how do we calculate these pHs? And this was on, I want to say 16.2, I think, that you guys turned in, and I'll have those back to you when I see you on Tuesday. So an example of this would be if I said, well, I had a buffer of HF and NaF, and then I added HCl. Okay, this one would be if I had a buffer of HF and NaF, but I added sodium hydroxide. So I added a base or I added an acid. I want to see what the pH is going to do. Okay. So if this is the case, this is just like a titration. Some of it's going to neutralize, and then you want to figure out the pH after that. So anytime you are adding an acid or adding a base to something that is already acidic or basic, you have to consider the neutralization first. Okay, so first is the neutralize with a BCA table. Okay, so anytime acid to a base, you have to do a BCA table first to figure out how much was neutralized. So what is the neutralization reaction? Well, if you're adding acid, it's going to react with the base part of the buffer. Or if you're adding base, it's going to react with the acid part of the buffer. So you have to pick the correct part of the buffer, but it should be obvious. If I'm adding H+, it's going to react with the base part, so the F- or A-, I guess I'm doing generic over here, aren't I? It's going to react with the A- and make HA. However, if I'm adding base, it's going to react with the acid part, and then those will neutralize to make H2O and A-. Okay, so these are neutralization equations, not Ka or Kb equations. So both of these are going to be like before, change, after. Before, change, after. Okay, so you got to figure out how much stuff is left. And then you can find the pH based on whatever's left over. So you don't have to do an ice table since these are buffers and they're probably still going to have some of both left in them. That's how you can find the pHs with the Henderson-Hasselbalch equation. So second, you're going to use your HH equation because it's still a buffer. Okay, just with your new concentrations of acid and base. So you can use your Henderson-Hasselbalch equation with your new concentrations of acid and base. And that's it. Now, if you go over, like say I added more H+, than I actually have base in my buffer, then I would just have extra H+, and you can find the pH from whatever H+ is left over. So I'll make a note of that here just in case. So if you're past the, really like the equivalence point, or if you're past the buffer capacity, meaning you used all of that part of the buffer capacity, use excess H+, and you can find your pH that way. Same thing down here. If you added enough base to neutralize all the acid in there, then you're going to be past the buffering capacity and you can find the pOH. So if past your buffering capacity here, you can use your excess OH- to find the pOH. Those are all the types of acid-base reactions. So you should be able to recognize what you're supposed to do when you read through a word problem for acid-base. Now, obviously, I cannot test you on all of these because that test would be like at least 3 hours